Hello and welcome to our video. Today we are presenting our SNS mini project on medical image processing and analysis. I am Krish along with my two teammates Harsh Lad and Anmol Katiyar. So let's start with the presentation. First is the methodology in the abnormal detection. This method leverages classical image processing theory to reliably detect abnormalities in X-ray and CT scans. It is built on principles of grayscale standardization and intensity normalization, enabling fair comparison of images from different sources. Denoising filters are carefully chosen to reduce noise while safeguarding important anatomical edges and details, since diagnostic clarity is crucial in medical imaging. Sharpening and contrast enhancement reveal subtle variations in tissue, which often indicate pathologies like tumors or fractures. Edge detection theory here via the Canny method enables identification of anatomical boundaries and automated segmentation, which objectively separates likely abnormal regions based on intensity distribution. Alternative methods for medical abnormality detection include machine learning based classifiers and deep learning, which can learn features directly from large annotated data sets. However, classical approaches, as used here, require less computational power, provide transparent and explainable steps, and offer easy manual adjustments, making them advantageous in setting with limited resources or a need for interpretability. This traditional method is particularly effective when clear intensity contrast exists between healthy and abnormal tissues, and its flexibility allows integration with manual refinement for even higher accuracy. Let's look at the formulas that were used. First is the intensity normalization. This formula scales images pixel to a standard range, ensuring consistent processing regardless of original image brightness. Next is the median filtering. This replaces each pixel with the median value from its local neighborhood to remove impulse noise while preserving edges. Gaussian filtering. This smooths the image using a bell-shaped kernel, reducing random noise while gently blurring the details. Unsharp masking. This enhances edges by boosting differences between the original and the blurred vision, making details clearer. Contrast stretching. This expands the pixel intensity range, so differences between the area are more visible, helping in highlighting the features. Gradient magnitude, that is edge detection. This measures how quickly intensity changes between pixels, helping locate boundaries or edges in the image. Otsu thresholding. This automatically finds the best cutoff point to separate regions by maximizing differences between classes. Area opening. This removes small isolated regions below a size threshold to reduce false positives during segmentation. And the last is image masking, that is region of interest. This applies a binary mask to show only the interested region parts of the image, hiding the rest.
This project detects abnormalities in medical image using a step-by-step image processing pipeline. The process includes pre-processing, filtering, sharpening, edge detection, segmentation, and optional region of isolation. Each step prepares the image for next, ensuring the accurate detection of abnormal region. So let's go through every process. First is pre-processing. Pre-processing prepares the input image by converting it to grayscale and normalizing the intensity. So grayscale conversion reduces complexity like normalization adjusts the brightness so the algorithm performs consistently. This separates a clean base image for further enhancement. The next thing is sharpening. Sharpening enhances important details inside the medical scan. By using filter like Gaussian and sharp masking, the image becomes clear and edge become more defined. This step restores fine details that may be blurred during filtering, making abnormalities easy to identify. The next is filtering. So we have used three major filters while using this process. So for removing noises and preserve the important instructions. First is medium filter. It removes salt and paper noises and preserve edges. Second, we have used this Gaussian filter that smoothes the image by reducing high frequency noise. Third is average filter. It smooths the pixel variation of a for a uniform appearance. Filtering ensures the image is noise-free, so edge detection and segmentation work accurately. The next step is edge detection. In this edge detection, uh, it identifies the boundaries and shape inside the medical image. Here we have used canny edge detector and is he- here we have used canny edge detector because it's accurate and noise resistant. We have told about Laplacian edge detector also, but as for higher medical images, uh, canny edge detection is highly preferred because it highlights organ boundaries, tissues, outlines, and unusual shape that may indicate abnormalities. This helps to guide the segmentation process. The next is segmentation. Segmentation separates abnormal region from normal tissue. Thresholding gate thresh plus embrace automatically selects the best intensity level to classify pixels. Monographically, operations remove small artifacts, fill holes, and refine the detected region. This step provide a clear mark showing abnormal areas potential. The last is the ROI masking or like uh, region of interest in which you can highlight or separate a tumor from a given image by using ROI poly in the MATLAB, which will enhance and zoom the region of your interest for specific purposes. Here you can see the result that we have performed. We have given a skin disease image and the code has detected the abnormal region highlighted by red. And we have also given a CT scan of a skull. And by ROI poly, we have removed the skull and keep the brain tissue.
Hello, so I'm Anmol and I will be discussing future scope for project. Early and accurate diagnosis. AI/ML will detect diseases earlier by identifying subtle patterns in X-rays, CT, MRI, and ultrasound, better than traditional methods. Automation of tasks, segmentation, classification, and image enhancing will become faster and more reliable, reducing radiologist workload. Personalized treatment. Combining imaging with patient data will help predict outcomes and guide personalized therapies. Real-time and smart imaging. AI will improve image quality, reduce scan time, and assist during surgeries and real-time imaging. Multimodal healthcare. The integration of imaging with genomics, EHRs, and wearables will give a complete picture of patient health. Remote and accessible diagnostics. AI tools can help provide radiology support in rural or resource-limited areas. New technologies, transformers, federated learning, synthetic data, and explainable AI will shape next generation medical imaging systems. Growing clinical adoption. More AI-powered devices will be approved and used directly in hospitals and radiology workflows. So, in conclusion, I would like to say the future of AI ML in medical image processing is extremely promising. Advancements in deep learning, radiomics, and multimodal data integration will enable faster, more accurate, and earlier diagnosis. AI will automate routine tasks, reduce human error, support personalized treatment, and improve clinical workflow efficiency. At the same time, challenges such as data quality, model transparency, bias, ethical concerns, and real-world validation must be addressed. Proper regulation, diverse data sets, and clinician AI collaboration, AI/ML can become a powerful tool that enhances, not replaces, medical professionals. Overall, AI/ML is set to transform medical imaging, making healthcare more precise, accessible, and efficient in the coming years. Thank you.